When we start discussing real zeros of polynomial functions, the following statements are all equivalent. We use a language interchangeably, and this kind of talks about that language that we're going to use when we start looking at zeros. So if we have a function f and a number a, sometimes we will say x equals a is a zero of that function f. We also say x equals a is a solution, or sometimes we'll use the word root of that function. Notice that we had to set that function equal to 0 to get that root or that solution, and that's where that word 0 comes from. Another way we can write these is we can say x minus a. Notice we put it in parentheses, so a changed sign. But if we write it this way, now we call it a linear factor of f of x. The last one that's up here is a point, a comma 0. A comma 0 is an x-intercept of the graph of f of x. So if you are a visual person and you like to graph these, you're looking for where it crosses the x-axis. These words in green we use interchangeably. So if they're asking for a 0, or a solution, or a root, or a linear factor, or an x-intercept, they're asking for very similar things. The last thing that's down here talks about repeated zeros, sometimes called multiplicities. They occur when you have, notice I have a linear factor here with a power. A would be my 0, and it repeats k times. So for instance, if I had something like x minus 2, 2 would be my root, or my 0, my solution. And if I had a 3 up here, there would be 3 of them. A multiplicity of 3. Negative 2 repeats 3 times. Now, something kind of interesting about this idea of multiplicity. Multiplicity models other functions. For instance, this one up here is an even function. There are a couple of places where it crosses the x-axis, and if you look at just that area, it crosses like a line. The line has a power of 1. But if you look right in here, it kind of looks like a quadratic sitting in there. It touches the line and then goes again. It doesn't actually cross. Because this area looks like a quadratic, that point, that 0, that solution, is repeated, and a quadratic has a power of 2, so it has a multiplicity of 2. Here's another example, this time using an odd function. We still have that one that looks like a line where it crosses the x-axis, but if you look right in here again, it looks like a mini quadratic, a power of 2, so that point would have a multiplicity of 2. My last example, still have that easy one. There is a root or a solution, the x-intercept. But take a look at what happens right in here. This looks like a cubic. Where it crosses right here acts like a cubic function. Cubic meaning 3. So this root, this answer, has a multiplicity of 3. I would expect that answer to be an answer 3 times in my function. So that's kind of how multiplicity or repeated zeros fits in with these real zeros, these x-intercepts, these roots, these linear factors, these solutions of powers. I'm going to briefly discuss the Intermediate Value Theorem. Here's the graphic we're going to use to look at the formal definition and the informal definition of how to use the Intermediate Value Theorem. The formal definition says let A and B be real numbers and A is less than B. So you can see that on our graph here, A is less than B. If polynomial f has f of A not equal to f of B, so now we're looking at my y values, notice they are not the same, then in that interval between A and B, including the ends, f takes on every value between f of a and f of b. So that means all the y values between f of a and f of b have to be accounted for between a and b. Now, another way to explain this, more of an informal way, but still using mathematical terminology, if we have 2 points, a, f of a, so that's this point right here, and b, f of b, which is this point right here. There are 2 points on the graph of a polynomial, and they are not equal to each other. That didn't change. Then for any number value between f of a and f of b, so I can pick anything between here, anything that's intermediate between these 2 values, there must be a number c between a and b. So that says I pick a y value over here, there has to be a corresponding value between those 2 numbers. So if I pick a y up here, there has to be a corresponding x value. If I pick something closer, there has to be a corresponding x value, but it's going to be something that's intermediate between a and b. Then f of c is between f of a and f of b. It guarantees that that exists. Now, we do use the intermediate value theorem, but we don't necessarily use it the way that it's defined formally or informally. The way we like to use the intermediate value theorem is this way. I included a picture and I included some table numbers down here. But notice that when I plugged in a 1, I got a negative value. When I plugged in a 2, I got a positive value. So that means somewhere between these 2, it actually crosses the x-axis. These are zeros. These are things we look for. Roots, x-intercepts, that number right there. If you are a numerical type of learner, we're looking at the y values going at -2, it's negative. -1, it's negative. 0, it's negative. But somewhere between 1 and 2, it changed a sign. So that means somewhere between 1 and 2, it had to cross the x-axis. It had to be 0 at some point. This is how we use the intermediate value theorem, is to find those zeros, those points of what x value is going to give me a y value of 0.
So let's take a look at the intermediate value theorem in action. I have my Texas Instrument graphing calculator out, and I have put in a cubic function. Knowing what I know about cubics, it should have 3 answers. This 8 being positive means that it's opening down to the left and up to the right, and it should have at most 2 turning points. Now, the nice thing about my graphing calculator is I'm going to show you all the windows at once. So when I turn this on, here's my equation, here's my graph, exactly what I wanted. I've got 2 turning points here and here, and it does look like it crosses 3 times. So here's the intermediate value theorem in action. Notice my x's are going up by 1s, and over here my y's start at -129, -23, then all of a sudden I have a +3. So somewhere between -1 and 0, it must cross the x-axis, indicated by this point right here. Also between 0 and 1, it changes sign again. So this point right here, between 0 and 1, crosses again, and then it goes from negative to positive a 3rd time. So somewhere between 1 and 2, it crosses a 3rd time, and after that, my numbers start to get very, very big. So the intermediate value theorem is helping me find those sign changes and know that there's an answer somewhere between those 2 numbers. Now, if I take a look at Desmos with the exact same equation, you'll notice that if I have my equation, my cubic right here, it happens to cross at 3 spots. These are the green dots on my Desmos. You'll also notice that I have a table of values here, and at -1 I've got this negative value, but at 0 I have this positive value. So somewhere between -1 and 0, it must cross the x-axis, and you can see that in my graph. Also, between 0 and 1, it goes from a positive value at 0 to a negative value at 1. Same thing that's on my table. So somewhere between -3 and +3 is 0, and that corresponds to an x value. And the x value is what I'm looking for. And those three x values fit in nicely between -1 and 0, between 0 and 1, and between 1 and 2.